We're back to talk more about electricity. And there's a question I'd left you with the day I did the Van de Graaff generator thing, and my hair stood up and I got shocked really badly. And I asked, how many volts was that? And we compared to like a 1.5 volt battery or a 9 volt battery or the 115 to 20 volt wall outlet thing. And it turned out the answer, about 300,000 volts. So how am I still in the land of the living after getting shocked by 300,000 volts? Well, it's simple if you know what a volt is, but you probably don't know what a volt is, which is why we're going to learn that right about now. First thing I'll say is the basic unit of electric charge. Electric charge, what are the units of charge? What is the symbol for charge? Well, the symbol is Q. Sometimes they use a big Q, sometimes a little q. The Q is the symbol for it. The unit it's measured in is the coulomb. Coulomb. Named after Mr. Coulomb. We just use the C for that, you know. So charge is Q. It's measured in coulombs, which is C. So we learned that. And a coulomb, is that a lot of electricity or a little bit of electricity? Well, first of all, don't call it electricity. Call it charge. That's the word for it. It's kind of a lot of charge. In fact, it's so much charge that if you had a coulomb here and a coulomb there, they would be pushing or pulling on each other with a force of 2 million tons or a million tons or something like that. Anyway, a lot. So a coulomb is a lot of charge. And yet, I contain hundreds of thousands of coulombs of positive charge, but hundreds of thousands of coulombs of negative charge. They're all doing their big force thing at the level of my atoms and molecules themselves holding my body together, making me actually be made of matter. You know, that's going on at a very small scale. Electrically, I don't do a whole lot to anybody. I might walk across the room and scrape my feet on the carpet on a dry day and get shocked or shock you. But that's just the tiniest little excess of one charge over another, you know, positive or negative or something. So basically, anyway, you got the point. Electric charge is measured in coulombs. There was another quantity we came up with. We had this idea called electric field. Electric field. We talked about Mr. Faraday. You know, electric field, the letter is E. It's measured in newtons per coulomb. The idea here is that one charge is fault, that another charge is getting pushed or pulled around. Of course, that one thinks it's that one's fault. It's mutual, you know. But you tend to ascribe this field to one of them and say that the other one is in the influence of that one's field. And it gets pushed around with a certain number of newtons on every coulomb. The idea is if you had more coulombs to get pushed around, you get pushed around more. So newtons per coulomb makes sense for electric field. Electric field's an important concept, but you don't hear too much about newtons per coulomb. Oh, you do hear about volts. And what the heck is a volt? Now, how do I want to introduce this? Well, through an analogy, of course, a couple of analogies. Bear with me. You know I like these things. So here's a thought, just bubbling up out of my mind. Imagine a society. It's like a parallel universe where we never invented electricity or the steam engine or anything. What if we were just still cave people, but really advanced cave people? So we're these advanced cave people, and we live in this cave. That's where we live. How do we live? Well, maybe we hunt or stuff, but I mean, we want some source of energy to do some work for us because it's so much work to just do everything yourself. This cave society was blessed with a natural resource, a huge pile of rocks at the top of the cliff. Big rocks, little rocks, all different size rocks, way up at the top of the cliff. And somebody noticed that if a rock fell, and it's easy to make a rock fall, you just take a stick and pry it loose and there it goes. Somebody found if the rock fell, you could let it hit a giant paddle wheel. So you got this big paddle wheel that gets hit by falling rocks. Somebody's job here is just to use a stick and tip rocks loose. And it makes the paddle wheel spin. And the paddle wheel's hooked up to all kind of levers and gears and belts. And it grinds your corn for you and sews your clothes for you. Anyway, this society has a source of energy from these rocks. They also have a waste problem because they're collecting this big environmental problem of rocks at the bottom of the hill. They've also got the resource problem of eventually they may run out of rocks. Maybe we have analogous issues with energy and the environment. But anyway, this is their version of it. But here's the thing. They want to know how much energy they're going to get from each rock. How much energy do you get from each rock? Well, they fall a distance h, and you know there's this gravitational potential energy that's mgh. We learned about that. Each rock has mgh. What if your job was to know how much energy you were going to get from every rock that fell? You're just a cave person. You barely got math. Pretty intensively computational there, computationally intensive to multiply all three numbers together. You might figure out after a while that the G, which is the 9.8 meters per second, or 10, and the H never changed. The only thing that was different every time you dropped a rock down was the mass. So, you know, you already painstakingly multiplied G and H together. Just leave that there as a quantity, all ready to have the last step done to multiply by the M. So it's like, what if you found out that, you know, what if G is 10 and H is, I don't know, say 50 meters, and so this is 500. And so it's like, hey, what's the next rock? 2 kilograms. Real quick. 2 times 500, that's 1,000. What's the next one? I got a 3 kilogram for you. Okay, then it's going to be 3 times 500, 1,500. Do you see how useful this little quantity is here? Where you say how many joules you get from every kilogram, then all you got to do is multiply by the kilograms. If the joules per kilogram, in this rather artificial example, I know I made up the society and everything, if the number of joules per kilogram is always the same, it's a handy number to have, joules per kilogram. So you just get your energy, which is what you really care about, by multiplying by the kilograms. Having said all that, let me talk about why you might want to talk about joules per coulomb. Maybe we're not a cave-dwelling society. Maybe we're a society based largely on electricity. Yeah, for the last 100-something years, we use electricity. It would be handy for us if we knew how many joules every coulomb had to offer, and then we could have that already and multiply times the number of coulombs we're talking about. The joule per coulomb, not the joule per kilogram. No, what if we had joules per coulomb? And we had a certain number of coulombs of charge. No, not fall off a cliff. I don't know, go through a wire maybe? Doesn't look the same, but it kind of is the same. Because these rocks had gravitational potential energy. The potential to get a bunch of energy or give a bunch of energy, use a bunch of energy, if they fell, you know, like that. Now, same thing with electricity. If coulombs fall from someplace they don't want to be to someplace they do want to be, like some positive charge hates being with these other positive charges. Love to be with them negatives over there. It falls. Now, it doesn't fall down necessarily, but energy-wise, it goes to a lower potential, like falling. So we would like to have a measure of the amount of energy per unit stuff, charge, not rocks, kilograms, but charge. So the joule per kilogram would be all handy, and we got a name for joule per kilogram. And first of all, the quantity is called electric potential. Now, we don't say energy because it's not the joules themselves. It's the number of joules each coulomb gets, joules per coulomb. So we don't say energy, we say difference. Electric potential difference. Now, the word difference is because there is a between involved here, or an across. There is a difference gravitationally between the top of the cliff and the bottom of the cliff, or a difference between the top of the cliff and where the cave is. That difference counts, right? Because the further the rock falls, the more energy you get from it that it loses and gives to you. So similarly, we talk about electric potential differences in energy. And when we leave the word energy off, we're talking about something that has a letter V. Why would you use a V for electric potential difference? Why not call it EPD, which you could call it, but that's quicker. Because we name it after people. This is named after Alessandro Volta. I'm not sure how my Italian was there, but anyway, an Italian guy named Alessandro Volta was the one studying this stuff, making batteries and things. So Volta, that's his name, Volta, got electric potential difference named after him. Not only did he get electric potential difference, the unit name, that named after him, they also named the volt after him. And the letter for volt is V. Now this is a little bit of a problem because we got the same letter for the quantity as we do for the unit form. Now that's not the case with charge. With charge we use Q for charge and C for the coulomb. That makes a distinction. For this electric potential difference thing, we use V for electric potential difference. And we also use V for the volt. I think most books will make this a capital uppercase V and this a small v. I think that's how they distinguish. If I don't make them different enough in size, we'll just do it by context. And the unit is called the volt. And guess what a volt is? I think you know already. It is a joule per coulomb. Every coulomb gets that many joules of energy. Now, this you get to understand better in context and usage of it. So we'll move on with what we do with this, and maybe it'll become more clear to you what it is. But what I'm going to do first is make a slight modification of my rocks on top of the cliff analogy, because there is something, a source of energy that people actually have used. Instead of dropping rocks, they drop water. Now, what does it mean for water to have energy? Well, how about a lake on top of a hill? There could be a big old mountain up here somewhere. There's a lake up on top of the hill. And it's way up on top of the hill. It's like a volcano. Gosh, you ought to see Crater Lake. Google it, Crater Lake, Oregon. Oh my God, it is beautiful. The water is so deep blue. It's where there was this mountain off topic. Hey, if I get off topic in class, I get off topic here. Back thousands and thousands of years ago, there was a Mount Mazama out in Oregon. And it was a volcano, and it blew up like crazy and blew cubic miles of stuff into the sky, probably devastated whatever was around there. And then a big hole. And it rained into the hole. And it made a lake 2,000 feet deep. So beautiful blue. I've been there a couple of times, maybe 3 times actually, 2 or 3. And then another volcano came up in the middle and made a little volcano that sticks up out of the lake. It's called Wizard Island. Please look up Crater Lake and go there one day. In any case, a lake up on a mountain has a lot of potential energy. If it's just sitting up there, not moving, it's static. Like static electricity is electricity that's where charge is separated. There's a potential difference. This charge would love to go there, but it ain't doing it right now. And that is static electricity. It doesn't do anything for you. And when you do little funny tricks with it, like get shocked, then it's a sudden, like dam burst like thing. It all goes at once or whatever. And you don't do anything useful with it except go, ah, like I did. But you could control this. You could use this energy. You could tap into this energy by having some sort of a little pipe or something, and it could go down, and maybe down here you make the water come out and it hits one. Oh, like a paddle wheel. In fact, they make these things. You know this, except they usually go to the top. Don't they go to the top? Oh, I forget. Maybe they go to the bottom. Like a river, like a mill. There's all these roads around Atlanta, this mill road, that mill road, because there was a mill on those roads. You notice there are creeks and rivers? Because water is flowing downhill, losing gravitational potential energy and making a wheel spin. And then you grind your corn, literally grind your corn. I wasn't even making that part up. That's what they do. And other things, do all kinds of things with a mill. You could use it to sew, all kinds of stuff you can do with energy. But if a society is using this energy, they're suddenly using something called current. Now, this is current of water, like current of river, but there's also electric current, which I'm also going to be introducing you to in this video shortly. But notice that the difference in the height here is really what matters. And the higher it is, the faster the water flows. Can't help but throw in another example. I used to go as a kid to Birmingham, Alabama a lot because I had relatives there. My grandparents lived there and my cousins lived there. And they lived about 2 miles apart in the eastern, northeast part of Birmingham. Anyway, we go to my grandparents' house, and if I spent the night there, get up in the morning, take a shower, and water comes blasting out of the shower. Yeah, it was good. But I went to my cousin's house, and it took forever to take a shower. The water would dribble out. You could hardly even get your hair wet enough to put shampoo in it, and then it'd take you like 10 minutes to rinse it because the water just dribbled out. Tied in with that, have you ever noticed how some cities proudly display their water up in big old tanks? Like, I know that I've been to Noonan before. I don't live in Noonan, but I've been to Noonan, and I've seen they have this big old tank, and it says, City of Homes. It probably also says Noonan. Is this like, look at our water, look how much water we have? Nah, that's not really the point. They keep it up in a tower. Why? Because it has a big gravitational potential difference between it and you with your shower or your hose or whatever. What makes the water come flowing out? The pressure caused by the big difference in the gravitational potential energy of being up here versus being down here, a difference. And now you might be able to guess why the water flowed out so slowly in my cousin's house. They lived up on a hill. Lived on Yellowstone Drive. I just remembered that. I don't know why I remember things like that. My cousins would be so proud. Anyway, my cousins lived up on a hill that was not very far below the water tower. Without much pressure, the current flowing through the shower was not very strong. My grandparents were down in the valley. The water came out really well there. By the way, you can also use electric pumps, to pump water. You don't have to do it this way, but they kind of do. And it's up in a tower, and you do that. At least a lot of it is. Anyway, having said all that, I've now, I think, made clear that electric potential difference is what's going to cause current to flow. And the more electric potential difference there is, the more current there is. And I have not said a common word yet for electric potential difference. It's a very commonly used term. And that term is, I'll put the quotes first, voltage. Voltage is electric potential difference. It's one of these cases where you can take a unit, stick age on the end, and act like you've just named a quantity. And you kind of can. Like, for instance, I could talk about acreage. That's the amount of acres. What the heck's an acre? It's what acreage is made of. Well, what is it? Area. It has a meaning. Footage. Footage can mean a lot of things. Sometimes it means like film, how many feet of film, see it's measured in feet. Tonnage, could be something's weight. Poundage, people won't say poundage a lot, but you could mean your weight. Yearage, nah, they just leave off the year and say age, right? But anyway, age just means the quantity that's measured in the units that came before it as a prefix. So voltage is not a real useful word if you don't know what it's all about. It's electric potential difference. And I'll probably slip up and call it voltage sometimes, honestly, but I'm supposed to be a good physics teacher and say electric potential difference. Okay. Now, having said that, what's the context? Okay, I'm going to do this, schematically, graphically, abstractly, whatever you want to call it, on the board first. Later, I think I'm going to pull out some of the stuff that I brought home that I hope works. When I left my room, I grabbed a bunch of stuff, wires and light bulbs and things. I'm hoping to do labby stuff with you, but I'll save that for a different video. Right now, see if we can introduce the basic concepts. Okay, what you do to make a circuit which means where you go all the way around and come back to where you started, circle, circuit, all the way back to where you started, is you start with a pump of sorts. This is the symbol for a battery. A battery actually can mean a group of cells. A battery kind of implies plurality, like there's more than one, but I won't think about that too much. We'll just call it a battery instead of a battery of batteries. But anyway, here's a battery. The symbol is you draw a long bar and a short bar, and you say this is the positive terminal of the battery, this is the negative terminal. In one sense of an analogy, kind of like you can do with water, it's a pump. It forces current to flow. Now, I'm also going to use the water tower analogy again because that gets gravity involved, like electrical, gravitational, we're going to talk about that. But this, okay, that's the battery. This is a wire. It may actually look like a wire because that's kind of how a wire looks. And while you could just do this and make a circuit, this would be called a short circuit because the word short, because it's kind of a short trip maybe, but it's also a very useless thing. All you're going to do here is make the wire hot and bring your battery down. Instead, you want the battery to be used to do something, like light up a light bulb. Now I'm going to put a little symbol here. Looks like a staircase kind of. Looks like an obstacle course. Some weird thing to have to get through. Got to do this, that zigzag, like those traffic cones or something. It's trouble to get through. It resists the motion of the charges. It is called a resistor because it resists. It tries to keep the current from flowing or forces it to pay a toll of some type along the way. Typically, it's probably like a light bulb. That's the example it'll be. Now, there's a lot of other things you can hook your battery up to besides a light bulb. You could hook your battery up to a little motor or all kinds of little devices that use electricity. But all of those devices, whether they're motors or light bulbs or whatever, are going to use the energy given to the charge that's flowing by the battery over here. So it's going to be, say, a light bulb. And the current is regarded as flowing like that. It's a round trip. It pumps it out, goes through, does its business over here, comes back, starts to go all around again. We say that the current moves in the direction that positive charge would be going. Like you'd have little positive charges going like that. Now, you might surmise, if you're really clever and really on top of things, you might surmise that's not quite really what happens because really in a metal, which wires are made of, it's those valence electrons hanging out like in the street that don't really have homes. They are the ones moving. So really what's happening microscopically, if you could see it, is you probably really got negative charges going the other way. But we just pretend that positives go that way. It's completely equivalent for macroscopic purposes. So anyway, that's what a circuit is. I'm going to plant another analogy in your head. I have a mental image of this where, I've been on a long road trip sometimes. Sometimes it goes into a little town in the middle of Kansas and there's wheat fields for like 100 miles in every direction. There's a little town. And I have a hotel, and I just imagine people get bored. What are you doing on a Friday night? I don't know. You can run around the wheat fields, or you could go down to the hotel and do this fun game where you ride up the elevator. Yeah, now I'm not calling it a pump anymore. I'm calling it an elevator. Why? Because it lifts you to a higher gravitational potential, right? A lot like a battery lifts charge to a higher electric potential energy. Very close analogy. The wires are represented by the halls of the hotel. So bored teenagers, I guess, I didn't really see this happening, but I'm just a crazy imagination. So they probably have better things to do. You could ride the elevator up to the top floor, like 6 floors up maybe, run down the hall, and then what the heck is this? Looks like a staircase. Could be a staircase. That's not a bad example. You can think of it as a staircase if you want to. However, I do have an analogy that makes resistor sound better. It carries a little further. There is a device or a piece of football practice equipment that I've seen outside. I don't know if they're using it these days. Maybe some of you play football, you know what I'm talking about. It's this gauntlet-like thing. It's a frame. And it's got these spring-loaded conical pads in it. And the idea is you got to run through it and force your way through these spring-loaded pads and end up going crazy like that. And people have to run through it one after another, and it resists their motion. It's hard to get through. Looks like it hurt. Slap, 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 slap. I've heard it called, I don't know if they call it that these days. Somebody a long time ago told me it was called the blaster. You run through and blast through it, and it blasts you on the way through. In any case, it resists your motion. Okay, these bored teenagers that rode the hotel in the middle of nowhere elevator up to the top floor, ran down, banging on guest doors, I guess, come around here, and there's a place where there should have been another elevator, but they removed the elevator. And instead of blocking off the doors, they left the doors open. That could be dangerous. So their solution is they went down to the local high school, got all the football blaster thingies, and lined the whole elevator shaft with spring-loaded blaster things. And that's more fun than ever. These kids come running down here, they jump into the blaster shaft, and they go down like this. And they get beat up kind of good, but not hurt too bad. And they go around for more. One after another. Wouldn't that be fun if you lived in the middle of nowhere? Yeah. So they run back to the elevator, they ride up again, get more potential energy, run down the hall, not losing any potential energy on the level hallway. In an electric circuit, you're not supposed to lose your energy in the wire. The wire is supposed to be a free and easy, very, very low resistance path. Maybe not no resistance, but not much. Then the fun starts. You jump in the blaster shaft and think about what happens after you've gone through. Those things are wiggling like crazy. What is this an analogy for? Heat. When electricity goes through a resistor, it knocks little molecules around or something. It hits stuff. As the electrons going through, the charges going through, hit things and knock them around. They wiggle, and that's hot. And if it gets hot enough, it'll glow. And that is called a light bulb. At least it's an incandescent light bulb. There's other kinds now. Is that it might be LEDs. I'm not sure, but all light bulbs are all that way. And you come back for more. You get it? Now, the flow of charge is called current. And that needs units and stuff too. So here's the deal. We have this thing called electric current. Electric current. It has a letter. For some reason, they chose the letter I, like a capital I, like me, you know. Current. The symbol is I. It needs some units. Now, historically, its units got defined early on, named after somebody. But in terms of what we've been saying, we need to relate it to the units of charge itself. This is a flow of charge. Now, if you had a flow of water, I think you would probably use something like gallons per second. Now, you could have like a river and have a big net across the river all the way to the bottom of the river, and where all the water had to go through the net, like you're catching all the fish or something. And the water that goes through that net could be measured in gallons per second. You could have the same number of gallons per second in a big, wide, slow-flowing river as you did in a smaller, much faster stream. You can still get the same amount of water through in a second, maybe. But you understand what current means in terms of water, like gallons per second. Here, it's, of course, measured in coulombs per second. Coulombs per second. Yeah, the amount of charge that goes through in a second. And it's named after somebody. It's named after Mr. I forgot his first name. He's French. Probably some accent marks in here I'm leaving out. Ampere, maybe it's got one of those. I didn't take French. Maybe got it right. French taking people, maybe. Anyway, Ampere is the guy who was named after. The letter, thank goodness, it's A. You say amperes, you write A for amperes. So that's the measure of how much charge is flowing. The current is measured in amperes, okay? I got to be done here pretty soon, but I'm going to throw in one more thing. I might as well get it in here, right? How much current is going to flow? How many amperes? Well, it depends, doesn't it? I know that water flows faster through pipes. Pipes, see now hallways, pipes, wires, all same thing. So water will flow faster, all other things being equal, if the water tower is up higher, or if the pump is stronger, however you want to look at it. In any case, I would think that the current would be proportional to, just ought to be proportional to the voltage, electric potential difference, right? That's a common sense thing. It's also empirically true, as I can probably test using like a voltmeter and some stuff that I can probably show you later. But the current also depends on this, doesn't it? Think about the very word resistance. If you resist more, you'll probably get less current. It's like taking your faucet and turning it almost off. If you turn it almost off, you're narrowing the little gap it can go through and providing a lot of resistance. Kind of hard to get through there, right? This word resistance, I'm introducing it through the example, resistance, viva la resistance or something, resistance, well, think about it. The current ought to be inversely proportional to the resistance, so more resistance would make less current. I would hope so. Otherwise, why call it resistance? Back to first week of school. You know what to do if you're proportional to one thing and you're proportional to something else. Told you that would come back. You'd say that I is proportional to V over R. Yep. Multiply, get married, fruitful and multiply. Yep. And then, and I'm almost done here. Almost done. Then, you see, I need a proportionality constant. Do you remember what happened when we found that F was proportional to MA in our lab with the bricks, accelerating the bricks? We found F was proportional to MA. But then we said, well, what's the proportionality constant? It depends on the definition of the units, or how you're going to come up with units for the thing we didn't have yet, which was F in this case. We had these. And we invented the Newton. A Newton is as a Newton does. What does a Newton do? It makes 1 kilogram accelerate by 1 meter per second per second. So I've got a golden opportunity. If I have not yet defined one of these units, well, I've already defined the units of I, that's amperes, and the V is volts. This is the one without units yet. Time to invent some. Units of resistance. If I invent them right, I can make the proportionality constant 1. If I play my cards right, it's easy to play them right. I'm going to say I actually exactly equals 1 times V over R. And I can do that if I define R right. So R is going to equal V over I. And the units need to be volts per ampere. I'm making this up, as I go along. So I'm just going to say it's a volt per ampere. And then the constant is 1 because I defined it that way. And we need a name. And it got named after Mr. Sounds like you're meditating. Ohm. Mr. Ohm. Yep. And what's the symbol for ohm? Bad joke. I know. I didn't make it up. It's not my fault. It's the Greek letter horseshoe. No, it's the Greek letter omega. Get it? Omega. Yeah, that's the ohm. That's the ohm. And then we have this law that says V equals IR. That's one way to write it, right? And it's called Ohm's law. Right? Got ohms in it. Tell you what, there's more to be said about ohms and Ohm's law And some of that needs to be found empirically, which means I probably need to get the wire and the batteries and stuff out. And this video's just gone 35 minutes, so I'll shut up right about now. See ya.